Okay folks, here we are back in Grass GIS and working with Wadi Hassa, still on project 2. Today we're going to cover least cost analysis in grass. So what you're looking at here, I have the Wadi Hassa site points up, and I have the you may have noticed that in the permanent you have the full SRTM, which is the square shape, and then you have one that says 30 meter clipped W shed, and that is one where I have already applied some hydrological modeling, like I showed you last week, to clip out essentially the largest watershed covering pretty much all of the Wadi Hassa area. Now a couple of the sites are outside of it down here, but for now I want to work with this today simply because a watershed boundary is an actual meaningful boundary as opposed to the square shape that we tend to work with, the rectilinear shape we tend to work with in GIS, simply because our monitors are rectangular. So that's the basics of what we're going to do. And if you remember last time, I pulled out a sample of Nabatean tower sites, and so instead of the whole survey database, I have it saved in a separate map set, which I have to find real quick. It is, for me, going to be in, I think in here, Nabatean Towers. Okay, so those are the sites right there that we are gonna work with. So firstly, least cost path, least cost surface, accumulated cost. These are the terms that I'm going to use a lot. And also cost, right? So cost is the actual value that it takes to cross over a cell. Sometimes you may hear this called friction, and it could be related to actual friction, it could be related to slope, it could be related to vegetation cover, it could be related to cultural or psychological costs of crossing, or social or economic or political costs of crossing through that region. But basically what we're looking at is to come up with a unit and to amalgamate all of the costs that the average person of the society you're modeling would have to accrue to cross one pixel. Now, the cost unit itself could be energy, like kilocalories. It could be something a little bit more esoteric, like political debt or some sort of dollar amount, an economic cost of crossing. But a common time that a lot of the routines automatically use, and that makes sense for a lot of reasons, is time, because it's fairly universal in the sense that you can look at all of these different sources of costs and come up with some kind of time penalty that you can apply if you want to amalgamate more than just the physical walking time to get across the cell from one side to the other. Now, in terms of how much cost to assign, there's two important things to think about. Firstly, the horizontal resolution of your DEM. We're working with a 30 meter resolution DEM, so any time costs that are physical in nature should be scaled to the time it would take to walk 30 meters over the terrain that is encapsulated in that single pixel. So we'll get at least one slope value or some other cost value that relates to how fast you'll be able to walk across it, and that will modify the walking speed, right? So let's say you walk at about 3 kilometers an hour. You do a little bit of math to figure out how many hours it would take to cross a 30 meter pixel. And I'm not going to do the math in my head right now, but it's probably something like 0.01 or 0.001 hours, because 30 into 300 or whatever it is, right? So that value would be if it was flat. Now if it's up or down or somewhere in between, we're going to modify that value so it would take a little longer to cross over it. If you want to add other sources of costs, they need to be scaled to the same unit, time, seconds of walking costs, or seconds of time to go across, that you add to that value, that physical walking value, Or potentially, if you want to keep this, if you want to deviate from like a realistic value, we just want a relative value, you could subtract, right, to make it more attractive. But it would be a number of additional seconds that you would add to the time to cross that cell, and you'd have to think about, again, we're working at a 30-meter resolution. What kind of additional cost is it? Is it a cost because the vegetation is thick and it's going to slow you down a little bit more? Well, on average, to cross the full 30 meters, how much is it going to take for thicker vegetation versus thinner vegetation? 10 extra seconds, 20 extra seconds, 100 extra seconds to cross that 30 meters. And if it's a more esoteric cost, then you have to be a little bit more circumspect. Again, indeed, if we're crossing a political border, how many additional seconds would it cost you in terms of being hesitant and worried about somebody seeing you in that area? And again, that needs to be scaled for that 30-meter horizontal resolution that we're working in. So all of these things you need to think about when you're entering into a least cost analysis. But we're going to keep it relatively simple. We're going to deal with just walking costs, and we're going to use these filtered sites as our starting point. So firstly, let me just show you the nuts and bolts of where this stuff exists. It's in the raster menu, as where many things are, and it's under terrain analysis where we've been working. And in fact, we have actually we have more than two modules that deal with least cost analysis, including creating the least cost path itself. R.cost is the isotropic one, and here you would have to calculate using perhaps Tobler's function or another function to create a cost map itself. At minimum, you could put in the slope value. So if we do that, I got to go back down to my terrain analysis. You see I have a lot more map sets on this particular computer. But let's just grab slope. And if you remember Devin White's paper, this is a real loose approximation of cost, but let's just do it anyway, right? And then we can put in our output map. We'll call this isotropic cost. Cost surface. And we can then put the directions. If we were going to do something with this, we could put those in. And we at least need a starting points map. Now there's 3 ways we could enter this. We could put in an existing vector map, so we could put in all of our tower sites, and I'll show you that when we get to the anisotropic one in a little bit. But we can also just put in the coordinates of a single starting point. We can also put in a raster points. This is literally just a couple of pixels in raster form. But let's grab our query tool, and let me just first quickly zoom in just randomly into one of these points. I'm just going to click on this particular one because it's centralized. It is site number, where is it? Site number 430, just for your reference. And we have the coordinates from where we clicked right here, like I showed you last time. So we're going to copy those, and we're going to go ahead and paste right into here. Boom. And we can talk about a few other things here. Again, the manual is your friend for all this stuff, but for now, we're just going to go ahead and run the routine. Now, I'm on a really fancy computer with lots of RAM, so I'm going to give it a ton of RAM. You're going to decide how much you want to allocate, but the more RAM you can give it, the faster it's going to go. And these operations do take some computing power, so if you're underpowered on your computer, come into the lab and use the lab computers, or set it and walk away and have your tea and stuff and come back. So I'm just going to hit run on that, and my computer here is going to do this relatively quick. Yours, again, will likely going to take a little bit longer. But r.cost will run faster than r.walk. And so basically, we'll compare it actually as we go back. So now we have our accumulated cost surface. And let me just zoom back out to the region. Now remember, our slope map is actually So I was going to try and stick with the watershed, but I realized the slope map that I put into this one is actually from the greater square region. And again, I have my computational region kind of zoomed in, so this is what I got going on over here. And if I put my Nabataean towers up, we can really see how that goes. So let's just change the colors on this so that it doesn't look like a DEM. I'm going to go, so this is our colors. I'm going to go to the Define tab, and I'm going to pick this Haxby color, I think. Let's go ahead and see how that looks. Hello. There we are. Boom. Okay. So if I put the legend up here, and as I like to do, I like to give it that little background so that we can read it better. And then I'm going to resize and move it and stick it over here like so. Okay, so what we're looking at is these are seconds of walking. Well, actually, no. These are accumulated slopes that you are crossing. Sorry, to be real careful, because remember, we just used the slope map as the input for this. And again, these are isotropic. Doesn't matter whether you're going upslope, downslope, or across slope. It's going to use whatever the slope number is to calculate the cost. So again, not the best value, but one that was simple enough for demonstration purposes. Let's show you how r.walk, which is the anisotropic cost accumulation function, actually works. So raster, terrain analysis, cumulative movement costs, r.walk. So here we have to put in the elevation map that we want, and I'm going to use the watershed version. Now we need a map containing friction costs. These are the additional costs to be added to the costs of walking. So again, these could be because of thick vegetation, or they could be fear of reprisal because you're crossing over a political boundary, or anything else that you wanted to put, but it has to be in units of additional seconds of walking time, scaled to the 30-meter resolution that we're dealing with in this particular map. For now, what I'm going to do is just put a uniform value of 1, but I need to create a map. This has to be a map. So I'm going to go into the raster. I'm going to get my raster map calculator. And what I'm going to do is to show you a formula to take an existing map and convert the values to something else. So we're going to use a Boolean formula. So I'm going to write if. That tells you we're dealing with Boolean. So we're looking for a conditional statement now. And I need a parentheses to open. And then I'm going to type it in, but you can look up the manual for map calc to see what these things are. Is null. That means if the value of the map I'm about to query is null, meaning no data, then that condition will come true. So now we're going to pull in our watershed, and basically what we're looking at now, if is null, this map, so all this white area is what we're finding now. We're going to keep that null. NULL with parentheses. That's the value to make a map value be nothing. Not 0, but nothing. Okay? And then the next comma says, so if this was true, keep it null. If it wasn't true, put the value of 1. So everywhere we have an elevation value that's not null, we are going to put the number 1, and everywhere we have a null value, we're going to keep it null. And then we have to close that first parentheses. And here I'm just going to call this friction. Okay? But I just realized I did something that you should not do, which is I'm working in permanents. So let me create a map set, and let's call this LCA. I'm going to call it LCA2 because I already have one in this particular database that I'm working in, but you can just call it LCA. Okay, so we're switching over to LCA2, which is okay. And now we're going to run this friction into that new map set. Oops, I meant to hit run. There we go. As soon as it's done, which it should be there, so it's all yellow, and if I was to query that map, we would see then we get the value of 1. No matter where we click, and outside we get no data. That's null. Okay, so that's friction. And now we can use r.walk. Where was it? Right here. Go back to r.walk, and we can put our friction in there. And then now we have to give it a name. So we can call this anisotropic cost surface. And here we could again also put that backlink direction map if that's an important thing that we want as well. And I still have those same coordinates, so I want to do this so I can show you what the difference is between the r.cost approach and the r.walk approach. So let's go ahead and do that. The only other thing is that here under settings, these are the coefficients that set the difference for walking upslope versus downslope, steep versus slightly shallow. And you would change these coefficients to change for a longer gait, somebody who's taller, somebody who has a shorter gait, somebody who's shorter, or perhaps for a pack animal or a goat or whatever thing that you wanted to put, you would change these particular values here. And you could also change this value here, the slope factor. But all these are set to the defaults like we read about in the papers, okay? The only other thing is to use the Knight's move. It's going to create a better output. Remember, it basically widens the neighborhood up when doing GIS's algorithm and looking for which next cell to move to when you're accumulating the costs across the landscape. And again, I'm going to crank up my memory on all of this, and I am going to hit run. And there we go. Went pretty quick on my computer here, and again, it may take a little longer on your computer depending on your resources. So we have that. Let's go ahead and change the color to that Haxby so that we can look at both maps in the same color scale. Where did that go? There it is. There we go. Okay, so here we can kind of just sort of go back and forth between them. Now the r.walk map actually is bigger, so the colors are stretched over a little bit more of an area. But let's zoom in a little bit and see if what we can see in terms of the patterning as we look at both of them. It's a little hard to see, and it may not come across in the video, but we're getting slightly different patterns as we move across the landscape because of the anisotropy or anisostropy. I don't know how to pronounce it correctly. The fact that we're taking into account slope, whether we're walking up it or down it or across it, and we're getting different cost values depending on the directionality of our movement. And that's important. Okay, so that was for using one input coordinate. We can actually put in all the points from this vector map or any other vector map that we've queried so that we get essentially a map where people are starting to walk away at the same time and accumulating the costs from every individual start point. So let's go ahead back into r.walk and let's go to the start tab. Let's delete that coordinate that we put in, and for our starting vector points, let's pick the Nabatean towers that we queried out, or whatever set of sites you are working with. And we're going to hit run. Sorry. Need to change the output map. So here we'll put Nab towers anisotropic cost surface. And we'll hit run. We'll let that do its thing for a minute or two. Okay, let me just update the colors on that to our Haxby. And again, you can choose whatever colors you want. I just picked Haxby because it has slightly more gradations and I feel like it pops a little bit more for this particular type of map. But again, you can choose whatever colors you want here. And as soon as we do that, I think we're going to be able to see that this is looking different, right? Remember, we're starting at every single tower site at the same time and the walkers are going out. And when they run up against each other, they kind of stop, right? But if they don't run up against each other, they'll keep walking out into the distance. And the further they go, the more the terrain is going to get averaged and the more round or circular it's going to look. But here in the middle, especially where there's lots of terrain, you can see how these relief of these catchment areas really changes their shape. So let me just turn off some of these other ones, and I'll show you real quick how we can very quickly first let's update our scale so that we get numbers that are meaningful for this map, because again they may be different across them, depending on whether we're using the anisotropic routine with actual seconds of walking cost or that one with r.cost where it was just like accumulated slope. So here these are seconds of walking time, and seconds are a little weird thing for our brain, so what you might want to do is to change this to hours, and again we can do that in minutes or hours. We can do it with the raster calculator. So here's our map calculator again. We'll put in our anisotropic cost service, and to get it from seconds to minutes we divide by 60, right, because there are 60 seconds in a minute, and we can divide that again by 60 to get it to hours. And just so that we know what we're dealing with, put that up there. I just copied and pasted it, and I'll put hours so I know that. And it should just make, the pattern won't change, the values are going to be different in it. I may have to change the colors again, so let me do that. There we go. And let's add a new scale for that one. So this is the hours map. We can see do all the things that I normally do. Okay, so now we can see a value that makes a little bit more sense for our brains, right? So this is seconds and this is hours. The patterns are the same, as you can see. We just changed the units to something a little bit more sensible. So the maximum distance is about 10.5 hours, but the transition from the dark blue to the cyan color, we're looking at about 3 hours of walking time, which is kind of an interesting zone, right? So 3 hours is kind of an interesting thing, and it looks like some of these sites are kind of buffering at that 3 hour kind of mark. So if I take our walking surface hours now and I go to the properties and I get derast and go to the selection, and now I can clip this map just visually so I can get a sense of it. So I'll start at 0 and I'll go to 3. So 0 to 3 means show me everything that's within 3 hours, and I can hit apply and it'll clip it out like that. So this is a 3 hour walking time buffer, not circular buffer, walking buffer around these collective sites. And if I want to go smaller, to let's show me the 2 hour, I just change that value, and now I get the 2 hour and I got the 1 hour. And I can click OK. And I got the 1 hour cost radius, walking cost, time cost radius around these sites. And here what we're actually seeing is that it's more that they're about 1 hour apart or less in the middle, and then these kind of outliers are kind of out there hanging out kind of far away from each other. Actually, sorry, 1 to 2 hours, right? Because there's 1 hour to here and then 1 additional hour to over there. Okay? So we could make this permanent, again, using our map calculator, which is still up in the background. And what we'll do is use an if statement. If our walking cost in hours is less than or equal to 1 hour, then we can, let's just make it a binary map, 1, otherwise 0. And again, 0 is not null, it's a real value. We could put NULL here if we wanted to do that as well. And here we can call this a, we can't start with a number, but we'll call it 1 hour cost radius. Just hit run. And once that chunks through, we will see it. There it is. 1 value is 1 if it's within 1 hour, or it's 0 if it's not. And we can do this, changing that number to 2, 3, 4, whatever we want, and we can make that map, binary map, as we want it to be. Okay, so one additional way to do this is to use an add-on that I created called r.catchment. So we would go up here to the raster add-on, or to the, this is G extension to add the extensions, raster, and then you find r.catchment and you hit install. And it'll do the little stuff over here, and it will install it, and then we can type it into the console here, r.catchment, like so, and hit enter, and it pops up. And what this will do, it will do pretty much exactly what we did here, but instead of using units of time, we can actually ask it to find a zone of particular square unit area. So let's say we're doing a catchment model and we need to know that the people who lived in this site need to have a certain number of square meters for farming. You put that value in right here. You basically parameterize it just the way we did with r.walk, because it uses r.walk underneath it. And again, here's the integer value for the catchment, 1, just like we did in the map calc. And we can check these things off. These are all the values from r.walk. And we can run through it this way. Now, we can start with the cost service that we've already created, and this should speed things up a little bit. But for whatever reason, you still need to put in the maps here, otherwise it just won't run. See these little asterisks? I mean, these are like required values. So we need to put in the towers, obviously. So we still need to put in the DEM, even though it's not going to do it. And here we're going to put our, let's just call this farming catchment. Oops. And I'm just going to leave the default value for now, but you can play around with the number of square meters if you want. And we're going to leave that alone. And we can put in our friction map here if we wanted to, but we don't need to do that. And we can also optionally say, let's only look at land that's less than 10 degrees slope, which is a commonality that most farmers are looking at, not too steep, right? And at this point we have enough where we can hit run. Oh, whoops. I guess we have to put this in. We do have to put in friction. There we go. Okay, so it's going to chug through. Again, it might take a little bit of time, but there we go. So we've got here a total catchment for all these sites that is equal to 5 million square meters. And again, these are tower sites, so these aren't farms, but you get the idea. And if there were areas that were greater than 10 degrees slope, they're being ignored. And it may not be if we do this. So let me just try this again with the overwrite and see if we get the 10 degrees ignored. This is a thing that I wrote, and this is interesting for me. I'm learning something. I'm going to have to go in and edit the code. So we get a slightly different result here. Okay, so that's important that we need to do that. Important things that we need to test on our own modules. Yeah, there we go. These are the 5 million square meters, but around each particular site, ignoring areas that are greater than 10 degrees slope. Okay, one last thing that I want to show you is that we can use inputs that are not sites. We can use inputs that are other meaningful features. So for example, let me just zoom out. We could use the location of known mountaintops or known water sources like springs or wells or something like that. And we can walk away from those, and that tells us basically the costs coming back to the sites. And it's roughly equivalent to knowing how far by foot it would take somebody to walk from a site point on the landscape to the destination, a water source or a mountaintop or a temple or something like that. For us, what we don't have like the location of springs, but what we do have is the streams that we pulled out. And if I can find that stream model that we did, it should be in terrain analysis, and we have our streams right here. Right? If we have this, we can use those as a starting point. But of course, what we need to do is you can't start from a line. It has to be points. The streams have those ending points and the junction points, but we want lots of points spread out across the stream. We could use a module to generate points along lines, v to points, and we would essentially tell it the distance we want between each starting point. That could work. But an even easier way is to simply turn the points into raster lines. And because we can start from raster points, technically each pixel is a point. And so if the line of the stream turns into a line of pixels, then each pixel is a starting point. And that actually is what we really want for this kind of analysis. So let's go to V to rast, vector to raster under map type conversions. We got our streams vector in the input vector, and the output will be streams raster. And the source values, it doesn't matter. We're just going to use this value because what we're going to do is this value right here is going to be the pixels 1. That's all we really want, right? So let's hit run on that, and it should go real quick. And as soon as it loads it up over here, we'll take a look. Okay, so let's turn off the vector streams behind there. We have these yellow raster streams, which you can see all across the map. And in r.walk, which is up here still in the background, we are going to go back to our required tab, and the elevation map is going to stay the same, the friction map is going to stay the same. We're going to change the output. We're going to call this streams and isotropic cost curves, because the starting point is going to be the streams. With the start, we're going to get rid of Nabatean towers from the start points, and in the start raster, we are going to pick our streams raster map that we created. And all the night move should be turned on. We can leave all of these things the same. We just hit run. Let it do its thing. And here we go. Okay, so now we have a cost map. I'm going to change it back to Haxby. So that we can see it. We have a map where the cost is the time to walk starting at all the different parts of the stream and just walking away upslope from those, right? And now we have our Nabatean towers, and we can query those values. We can query those values into our Nabatean tower vector map. because my Neptune Towers is in a different map set, I would have to make a copy of it. So let me just do that real quick. I'm just going to copy it, and I'm in my LCA2, and paste it in there. So I've made a complete copy of my Neptune Towers vector points from that other map set. You may need to do this as well, since this Neptune Towers is probably in your terrain analysis from last time. But now I can do my query with the update attributes v.what.rast, like I was showing you before. We're going to grab here our streams anisotropic cost surface, and we're going to create stream cost seconds. And of course, we could convert this to minutes or hours the same way we did with the map calculator first if we wanted to do that. We can hit run. What did I do here? Oh, this is the problem. Visibility. I picked the wrong one. Should have called it something different so I would know that we want the one from LCA2. So now we hit run. Parameter column, that's it. Oh, erase that. Streams cost sec. And it could be, let's put W cost so we know that this is walking costs. Here we go. Now let's take a look at our attribute data, and the column will be put way at the end over here. So here we have stream costs. Oops, must not have finished yet. Refresh. Oh, because I'm still in the visibility one. Hold on. Let me do things the right way, Professor Ula. Here we are, LCA2. I'm going to add that and remove the other one. Okay. So now, all the way at the end, streams walking cost seconds over here. Now, if you follow along in the project file, I want you to compare this value to the linear straight line. You'll have to do a little math with some sort of walking speed to be able to do that, but you know, to query the straight line to the costs, we are going to go back into the vector menu, and we're going to find that nearest features v distance. Can't remember I showed you this last time, but we can do it again real quick. And the from is going to be our Nabataean towers in the correct map set, and their points, and we want the minimum distance, and our to is going to be our stream vector map, which is lines. We don't want the points there. And we need to create the new column because for whatever reason v-distance doesn't have the ability to create columns. Where's our attribute table? There it is. Okay. So let's go ahead and add a new column right here called streams Euclid. Oops. Euclidean distance, like so. And we can hit add. Oh, technically that should have been a double. So let me remove that. And add that as a double. So there it is. And we can bring back our v distance, and now we can put that one in here. Let's see if it finds it. It might not find it because this was up before we added that. And I can see that I misspelled stream, so I'm just going to roll with it. There we go. Okay, so now back under the Browse tab, and we refresh it. Hey, where are you going? It's thinking about it. You know, sometimes I find that you just got to close it and reopen it faster than trying to hit refresh sometimes. And there we go. So again, these are meters and these are seconds, so now we have to convert it. How many seconds will it take for you to walk? And you just do some math in the column to convert it. And easiest way is to do what I showed you last time. You basically export the attribute table to a CSV, and then you can use a spreadsheet to do it. But it is possible to edit the values in the column using this VDB update. So it's database, vector database connections, change values. And in this particular case, we would want to get that value over here, Euclidean distance, and we would put in the formula over here. And if I have to think about it for a second, so we would grab the column like this, and we would need to put the walking time in seconds. So let's say 3 kilometers an hour, that's 3,000 meters for a good number of seconds. Hold on, let me just do that real quick. 60 seconds in a minute times 60 minutes in an hour equals 3,600, and we have 3,000 meters per that many of seconds. We get this value right here of 0.0883. So we just multiply the linear distance in meters by that. Now I'm doing something a little bit dangerous. I'm going to overwrite this column. Ideally, I would make a new column and write these values into it, which would be here. In fact, you know what? I'm going to do it the right way for you guys, not the way that is the easiest at this moment. Okay, it looks like the attribute table is not open, so we'll open that again. We're going to go ahead and manage tables, make it a double. We're going to call this stream Euclid seconds. Okay, I'll add that. And now in my so many windows, where is our, these colors can be closed, make it a little easier for me to find something. VDB update, there it is. So now, it's not going to show you the new column again, so we're just going to have to type it in. Stream, let me just scroll it down so I can see this. Stream underscore Euclid sec. Now I'm going to hit run. There we go. So again, I'm just going to reload the column, the table. Show attribute data. And here we go. Right? So these are the seconds. Now this is really interesting. You can see it takes a lot longer to walk along the train than to fly in a direct straight line at 3 kilometers an hour. Okay? Alright, I'm going to end that here, and we will pick up next week with visibility analyses.